Welcome to the 18th lecture for Physics 4B and our first lecture on magnetism. As we introduce magnetism this week and in the coming weeks, I hope you will find many of the concepts and tools we introduced in the context of static electricity useful. As you will see by the end of our semester, magnetism is closely intertwined with electricity, and the many close parallels are not accidental but deliberate. For this introductory lecture, we start with an introductory segment on magnetism overall, pointing out the things you already probably know. But our focus will be on things that often don't get covered in earlier science classes, starting with the most elementary magnetic interactions. In order to describe these elementary interactions, we first need to review the cross product. While we introduced the cross product back in Physics 4A, I find that many students can use a timely review, and the degree to which we rely on the cross product here in Physics 4B is far greater than how important the cross product was in Physics 4A. Not very. We also have new physical laws that use the cross product, which means more examples. And speaking of examples, we will look at examples of magnetic forces on current-carrying wires, which forms the basis of the electric motor, which we'll come back to after covering more laws of physics that we need to cover this device completely. And we will look at some more illustrative examples of magnetic forces on moving electric charges. And finally, we wrap up this lecture with the Hall effect, which can be used to determine the sign of the charge carrier of a conductor, and more interestingly, semiconductors. With everything you may be working on this week, we have this one lecture this week on magnetism. Next week, as we continue our study of magnetism, we will look at how these magnetic fields get produced. Again, in the fundamental, most elementary way. Welcome back. So we are starting with the new topics today with magnetism. And magnetism is a little bit weird. In some sense, you guys have more familiarity with the magnet. As in, most of you kind of remember playing with the fridge magnet, and it doesn't, it doesn't surprise you that, to start off with, how many people know what this is? What does it look like? It kind of looks like propeller. It's compass, as in, right? And it doesn't surprise anyone when I push it a little bit and let go, that it kind of comes back to where it was, right? Can someone say what compass is for?
It allows you to know the direction of the poles up on the Earth.
Yeah.
It allows you to travel
Direction of poles. So people use for navigation for thousands of years. Anybody here know which direction is north in this room by chance?
No.
That way? Okay, so this must be the North Pole. And
No. North,
what?
because that's the Bay Area. The Bay is here. So
Let's see. I'm trying to imagine the map. So Science Annex is here. The campus is to the west of Science Annex, right? So north. Okay, so the blue end must be north. And it doesn't surprise anyone that when you see this thing suddenly moving around, you don't think I'm, performing magic tricks or anything. Magnetism, in some sense, you are already familiar with it. And when I take this bar magnet, which already has north and south label, so we figured the blue end must be north, and it repels from north, attracts to south, or south and repels from south. All of this seems familiar to you, right? So I say magnetism is weird because, so let me, by the way, pass this around. I'm going to pass one more thing around, but figured, why do I get, sorry, I don't know what else you would do with it here. Let me send around another magnet with it. Here's the neodymium magnet to go with it.
so that you have something to do with, I don't know. So, in some sense, you're already familiar with all this stuff already. And this picture is something that illustrates something that many of you have probably seen. So what this overhead camera is showing right now is just, so these are just the array of tiny compasses that you have seen. And when I bring this bar magnet around, what you're able to see is that the bar magnet affects the direction of these tiny compasses as I move it around. And if I put this in the center, does this picture look familiar? Like you have seen before? Yeah, you have, many of you have seen this even before we did any electricity. And it kind of resembles the electric dipole field, but as we mentioned when we were doing electric dipole, you have kind of seen this before, right? So, yeah, so, in this sense, a lot of the introductory material for magnetism, it's something that you have seen before, just by nature of having gone through education in the 20th or 21st century. And, none of this is new. And let me just do one last thing. This is one of the demos I found in the closet, and it's kind of a cool demo. I'll pass this one around. This is the cool one that, it's something that you can imagine, but you maybe not have seen. So this illustrates electric or magnetic field in 2 dimensions. It kind of looks like electric field you have seen before. This can be used to illustrate magnetic field in 3 dimensions, because it's a solid 3-dimensional object. I can try to show it to you on the overhead thing, but it's not as impressive there as to seeing it yourself. So first you have to shake it to distribute the iron filing evenly around. Once it's down there, oops. Then what I have to do is before they settle under gravity, I have to kind of put this in the middle. And you can maybe see, I don't know, this is why I thought it would. Can you kind of see the iron filings gathering into the dipole field pattern? And because this is 3D, if you kind of turn it around, then you can see what the magnetic field looks like in 3-dimensional shape. So let me pass this around. The way I recommend that you do it is, first to shake it. You have to evenly distribute the iron filing. It'll settle into the, pictures that don't look as good. And then, put in this magnet in here and see sort of the kind of shape that forms. So it's a fun demo. I have it, so might as well make some use out of it. So, all of this you have seen before. Nothing here is all that surprising. So let's start out with some definition of terms that we are going to be using. So we should define them so that I can make sure everyone knows what I'm talking about when I do that. So let me just write down some magnetism terms. So I guess the term I want to start out with is magnetic field. And when I mention magnetic field, if you are thinking of electric field that we have talked about before, it'll be a good place to start. So for now, I don't really want to define magnetic field quite yet. We'll get to it. But for now, for your intuitive feel, I want to say it's similar to electric field, except that it's dealing with a magnet, right? So when you're dealing with a magnet, so this magnetic field, which you can see here, so this is the visualization of a magnetic field, as in you can imagine following these lines and drawing the magnetic field lines the way you have drawn the electric field lines, right? That's why we spent so much time on electric field, because the intuition you build for electric field will also be relevant when you're dealing with the magnetic field. But field is a bit of an abstract quantity, as in the orientation of these tiny compasses. They illustrate the magnetic field, but these tiny compasses are not magnetic field themselves. It's like with the electric field. Once I place a magnet in space, then just because there's a magnet here, that modifies the space around it to have that magnetic field. Whether you have something in that space, like test charges in electricity, something in space to illustrate the field or not. The field simply exists there, whether you have something to see it with or not. So with the electricity and electric field, we said, electric field interacts with electric charges. And the expression that we fell on many times was, electric force is given by charge times electric field. So what we want to have a word to describe it is, what does magnetic field interact with? Magnetic charge? So let's just start out with just the magnet. If you are talking about, that this magnetic field interacts with magnet. When I talk about magnets, what do you imagine in your head? Like, wait, where's my bar magnet? Oh, okay. The bar magnet that KD is holding, is that more or less what you imagine when I talk about magnets? Right? So when you have a magnet, it has, it has two poles. It has north pole and south pole. So it has these two poles. And I guess there's a reason we call them poles instead of, instead of using the same word we used in electricity. In electricity, we would have, so let me draw the analogous version in electricity. When we were dealing with electricity, we had electric dipole, right? And when we had the electric dipole, we had a positive charge and negative charge at the two ends. And in a dipole configuration, we would talk about how far they are separated. And this whole thing combined as a whole would be an electric dipole. But except when we are referring to this particular combination, we would call this object electric charge. So the question is, why do we use a different word for this? Why do we simply not say it's a north charge and south charge? Like, in other words, how is magnetism different from electricity in one key way? This is something I hope you already know. I'm just trying to highlight it. But magnetism is different from electricity in one key way. Strength, you mean? Strength. Oh, they're about equally strong. Okay, it depends on, let me put it this way. Electric force can be as strong as, magnetic force can be as strong as electric force. So in terms of the strength of interaction, they are about the same.
So can we say they're a flow of energy in a dipole where they're in a...
Everything has energy. It's something more fundamental, something that you already know. If you play with any kind, where's my compass? Oh, okay, I kind of need that for my next illustration. So you guys have played with the compass and, a magnet that came with it. So you've seen that one end either attracts or repel the other end, right? And what we've seen before was that the blue end was the North Pole. So if I have my magnet here, if I have magnet here, then the North Pole would repel the North Pole of the compass. And all of this is similar to electricity, as in like poles repel like, or South Pole repels south. Wait, is it repelling? Huh. You might have got, South Pole repels south. Some of my compasses are demagnetizing. And the North Pole attracts the South Pole, or vice versa. South Pole attracts the North Pole. Okay? Now, here's something you might have seen as a child playing with a magnet. So this magnet is actually broken. I keep trying to hold it as one piece, but it is broken. When you break the magnet, now so I have a North Pole, and I want to use this North Pole to attract or repel the North Pole there. And when I try that, this is what I get. It actually attracts. What happened? I mean, I'm holding the North Pole, but why is North Pole attracting the North Pole instead of repelling it?
Now it's split again, so now there's another South Pole.
Yeah, this end is still the North Pole, and the bottom is actually now a South Pole. So if I make sure to bring the top end closer, then that'll repel the North Pole. But if I turn it around and bring the other end, this is actually South Pole now. Like everyone knows this, right? I'm not telling you anything you don't already know. Yeah, I won't ask because I'm not trying to embarrass people. But if you didn't know, then you should know that there's something funny going on with the magnets that wasn't with the electric dipole. So with the magnets, if you imagine breaking up into two pieces, then there's north and south within the material. So, I was asking why do we call them poles rather than charges? One of the reasons would be this is how you always see magnet. You never see North Pole by itself. You never see South Pole by itself. If you were ever to, you would actually call that monopole. And magnetic monopole is actually a pretty interesting topic of research. People have been looking for it for a long time. There were a couple signals that people could not reproduce later. Magnetic monopole is something interesting to look at if you're interested, but we're not really going to get into that. For the purpose of this class, every time you see a magnet, it occurs always as a combination of north and south. So this is what we are used to referring to as a magnet is what we would call, to be technically complete and correct, what we would call magnetic dipole. And almost everything about magnetic dipole is similar to the electric dipole. The one difference is that in electric dipole, you could imagine separating that. You could imagine taking positive charge, and that's it. You turn the electric dipole into electric monopole. Like, that's nothing unusual. But with the magnetic dipole, you cannot do that. If you try to separate, this will just become dipole on its own. None of this is surprising, right? So, so in terms of qualitatively dealing with the magnets, a lot of this is what you, once again, already know. But I started by saying that study of magnetism is a little bit complicated, strange, in the sense that if I'm talking about very qualitative description, it's something that you're already familiar with. In fact, I hope you have better intuition for this stuff than you did with electricity, just from having seen it more. But once we start getting into the fundamental description of magnetism, as in the kind of stuff you really cannot cover in high school physics, maybe you can do, depends on your teacher, can't really cover in high school physics, and definitely not in middle school or before, it gets more complicated. So for electricity, I had this simple expression that I could write down and could always refer to. As in, if you're ever confused about electric field, think about this. You understand force, this is how you get electric field. I will not be able to write down a similar expression for magnetism. So it's not as though I can write down, magnetic force is equal to some magnetic charge times, I'm going to have to introduce a new symbol for magnetic field. We use a symbol B for magnetic field for some reason. I'm not sure why. So it's not as though I can write this down. This is wrong. Any guesses why that would be wrong? Like why I wouldn't even bother trying to guess that expression that magnetic force is equal to, charge times magnetic field? There's no magnetic charge, right? So it's not as though that's really why. Now, if we had magnetic charge, then this would work. But we don't have magnetic charge. So we have to somehow describe force due to magnetic field that's not on a magnetic charge. It's on something else. So, I mean, we could talk about force on a, magnet. That's what we are describing here. And that's the experience you are familiar with. But, I'll tell you that magnets are complicated. It's so complicated that we are really not going to get into magnetism of material all that much. But I'll tell you that magnets are complicated. It's so complicated that we are really not going to get into magnetism of material all that much. I should mention these three words so that at least I can say that I have mentioned them. It's not, once again, this is not something we are going to go deeply into, but when we talk about magnetic properties of materials, there are three words used to describe how a particular material, how a particular atom or molecule or particular material responds to magnetic field. We call them diamagnetic stuff. This is what you would expect sort of using classical physics. And I'm guessing it's most common. I don't know, I'm not a material scientist. And there's something called paramagnetism. So there are things that are paramagnetic. And the final thing is something you might have heard before, just because it comes up in everyday life from time to time, something called ferromagnetic. So this is one of those places where if you are one of those students who do well in spelling bee, then that would help you with these. Versus something no longer being ferromagnetic above the temperature. All of that is actually getting to why that happens. That's opposition material. Describing that those things are there, I'd rather leave that to your reading than spending a lot of class time. So this is maybe the first of the things that says magnetism is somewhat complicated. That even though it's something that you are more familiar with than electricity, it's trying to treat magnetism like the way we treat everything in physics, as fundamental, basic property of nature, it already gets complicated. So what I want to start the proper coverage of magnetism in this class is what's the sort of the basic unit of interaction with magnetic field, which we are going to say we have it somehow. And in next Wednesday's class, when I'm getting evaluated, that's when we are going to talk about the fundamental source of magnetic field. For today, we'll say we have magnetic field somehow. I mean, we know where to find the magnet. Here's a magnet. So I know how to get my magnetic field from a permanent magnet. And for today, we are simply going to say, all right, how does this magnet interact with some other fundamental entity so that we can base all our understanding of magnetism on this. So we are going to start by saying these magnets, they're not fundamental because sort of, it's macroscopic object. And so this is not the fundamental object. And if we try to get down to this level, field interacting with the charge to produce a force, well, we don't have magnetic charge. So this is a very puzzling thing. And unless someone here happens to know the answer, what's the elementary object in nature that does interact with the magnetic field? Yes, no? So I will reenact one of the experiments that were done in the, I guess, early 19th century. It's I have to imagine it was an accidental discovery. Actually, the accidental discovery, it happened the other way. People were observing the interaction with magnets with this other thing, but I don't really have the tools to demonstrate that. So I'm going to demonstrate the flip side of that interaction, where you have a strong magnet already, and something that you can describe as in terms of some fundamental object, elementary object, interacts with this magnet. So right now I have this magnet here And let me move this camera so that you can see it better. This is some setup I have with the wires and whatnot. So when I move this magnet around, you don't see any interaction with this wire, right? And does that sound like that's what you would expect? Yes? Yeah, wires made out of copper. Key thing is that it's not ferromagnetic. I forget if it's diamagnetic or paramagnetic, but whatever it is, it's a very weak interaction. That's why you are not seeing any force. When I move this, you don't really see any interaction here. Yeah? Now, so that's true of copper wire and just a magnet. But what happens is, let me turn on this power supply. Can everyone read that it's outputting 0 current? Right? So what I have here is I have wire, the black wire here connected to the negative terminal. And I have this red wire connected to the positive terminal. And I have this end open so that I can briefly touch it to let current flow. So let's see what happens. Oh, maybe I moved the wire. Oh, that's why I taped it down here. I want you to make sure that I don't accidentally move the wire. Let me just tape it down one more time to make sure that when I'm touching that end, you have some reasonable assurance that that's not what's moving the wire. So, all right, tape it down one more time. So, even though I'm moving this, okay, that shouldn't move the other end. All right. Now, let me touch this end. So I guess you can't really see it in the camera, but when you look at the screen, you will see this portion of the wire suddenly move. Then that matches with when the current starts to flow. Like, that number, it goes from 0 to 3. That's sort of the maximum current my power supply can provide. So when it has 0 current, nothing happens. When the current starts to flow, then the wire suddenly moves. And what's more fun is I can change the directions. So let me take this magnet and turn it around. So, I don't know which end is North Pole. Probably should have figured that out. Is it moving in the same direction it did the last time? No, it's moving the other way, right? So, so any guesses? How would you describe the elementary object in nature that interacts with this magnetic field that's coming out of this magnet? Electrons. The electric charges are somehow interacting with this magnet. Now, it doesn't interact all the time, as you can see. Right now, it's not interacting. It's not doing anything. It interacts only under certain circumstances. So let me do a couple things to describe them more carefully. I have to kind of label this. The blue is the North Pole, right? Let me see. OK, so this is repelling the blue end. So this is my North Pole. Let me write N on it. OK. Double check. All right. So this is my North Pole here. Let me do this experiment one more time. So yeah, you kind of to imagine that this is your right hand or left hand side and the right hand side. So when I let the current flow, then it jumps over to the side. All right, so let me try to draw this picture on the board. So I have my North Pole here, which produces magnetic field that I'm going to illustrate this way. And what I have set up is I have set up a current that flows from left to right. So I have a current that's coming in, flowing through. So if we insist on describing this as some sort of interaction with the electron, which direction is electron flowing? Left to right or right to left? Once again, so I'm describing my current as flowing from left to right. Yeah, because electron is negatively charged. That's the convention. That's just the convention we have to deal with. So what this means is I have electrons that are moving from right to left, according to the description we have. So, so I have two kind of things that are describing some sort of direction. Magnetic field pointing up, and I guess electron velocity pointing to the left. What direction is my force? Based on what you see here. Does the wire jump up or down? Does it really jump up? Jumps sideways, right? So it's not really jumping up. In fact, let me do this. I can change the direction of current instead. So if I just flip this around here, then I can change the direction. Wait, can someone remember which direction the wire went? Okay, came towards me, right? So when I flip the direction of current around, oops, then it goes the other way. But in both cases, it goes sideways. It doesn't go up or down. So, all right, it's going sideways. Is it going in the same direction as the direction of this electron velocity? No, because if it's going in the direction of the electrons moving, it would get pulled or pushed this way, right? But that's not what it's doing. It's going perpendicular to that direction. So on this board, let's be careful. So we are saying this is left and right. And you're kind of looking at the board. So the direction of the force, is it into the board? Or, yeah, it's into the board, right? Yeah, so that's the direction of the force you get. In this picture, yeah, right? So this is left to right. Wait, so I need to flip it around. So if I'm drawing it, yeah, so if, let me do it another way so that, let me arrange this in a way that from the way you guys are looking at, the current is flowing from left to right. So this is the positive end that, current comes out over here, flows through here from left to right. So when the things are set up that way, current, the wire gets pushed that way. So the force in this case is coming out of the board. Okay? So in this picture, this electron, as it flows through, you get the force on that electron is out of the board. Okay? So this is what I mean, magnetism is complicated. Even trying to figure out the direction of magnetic force, well, it doesn't go in the direction of the magnetic field, apparently. If you're trying to describe the elementary interaction of the magnetic field with the electric charge. And one of the things that seems to affect whether there's magnetic force or not, let me put a little symbol. B is the letter we use for magnet. Oops, it isn't for some reason. So, sorry. All right, so when you look at the, so if the electrons are not moving, if there's no current, then there's no magnetic force at all. So having this charge moving must be an important part of it. And when you get there to be a force by causing current to flow, then the direction of the force once again doesn't seem to have anything to do with the velocity, because the force is not going in the direction of velocity either. If it was has something to do with the velocity, you might be able to get some sense of intuition using friction force. Friction force usually goes against the velocity, but it's nothing like that here either. So it comes down to we have to somehow relate the. So we are trying to describe the elementary interaction here. Somehow this magnetic field, which points up, and this velocity vector, which in this case points to left, because it's negative charge flowing to the left. Somehow I have to be able to combine these two vectors to give something that's coming out horizontally out of the board. Have you seen any mathematical operation or description that gave you this kind of description? You have two vectors, one pointing up, one pointing to the left. And by combining these two vectors, you have something. How would you describe the direction of this vector relative to these two? Yeah, you skipped a couple steps. How would you describe the direction of this vector to these other two vectors? Perpendicular, right? That's what you're saying. Okay, why are you guys whispering? So perpendicular. So this vector is perpendicular to both the magnetic field and it's perpendicular to the velocity. And as Crystal was saying, you know one kind of mathematical operation that gives something that's perpendicular to both of the inputs that are going into it, and that's cross product. So this is going to be how we describe magnetic force. So magnetic force, the very basic expression for magnetic force is, so we are describing force due to a magnetic field on some kind of charge. And it's not going to depend on just remember this is electric charge, not magnetic charge. It doesn't just depend on the charge, it also depends on the velocity, what kind of velocity it has. And I guess if I'm being complete here, it also depends on the magnetic field. So the equation for this vector force is going to be electric charge times V cross B. The velocity vector cross magnetic field. And that's what you are seeing here. I have set it up so that current goes from left to right, and from the cross product, current cross the magnetic field, force goes that way. Wait, but isn't the velocity pointing to the left? If you are doing cross product of V cross B, doesn't that go into the board? Why does force come out of the board? So you are saying that if instead of we had this electrons, if we had a positive charge that's going in the same direction of current, then that would make sense, right? But is this what we really have? No, this is what we really have. So we want to make sense of this expression using what actually does happen. By the way, before maybe we go into this today, how many people need a review of cross product and right-hand rule? Yeah, I find that most people do. We do cover it in Physics 4a, but for some of you, it's been a while. And for many of you, the first time you covered it, you didn't really get it. And you figured you could get through the class without it. But I will tell you, with magnetism, even the very fundamental interaction is stated in terms of cross product. And when we get to how magnetic fields are produced, that will also involve cross product. So what it comes down to is that if you feel like you are not solid in understanding of cross product, it's like trying to get through, trying to get through the rest of physics when you don't know how to multiply numbers together. So it's that important. So I thought we should actually spend a little bit of time going over cross product. Yeah. So let's actually take a short break now, and when we come back to that, I'm gonna give you a shorter break. Come back and by 1:56, please. So let's go over this cross product thing. You have seen it first time in Physics 4a, but once again, the reason I'm taking time to do this is in Physics 4a, you could have actually gotten through most of it if you felt you didn't understand cross product. It wasn't that important. It wasn't that important. But with the magnetism, if you don't understand cross product, then you might as well give up now because the rest of the class until the end of the semester won't really make all that much sense. So let's go over cross product. As you recall, cross product is how you describe multiplying two vectors together. So you might say cross product C is a result of multiplying two vectors, A and B. A cross B. And for sake of clarity, let me draw sake of concreteness, let me draw a representation of vector A and a representation of vector B on the board. So I'm going to take care to make vector A point downward so that I don't accidentally do Nazi salute. So this is vector A. And vector B, it can be going many different ways. Let me just have it go this way. So these are the two vectors that I'm looking at to get a cross product. So let me quickly go through the exercise we did in Physics 4a to try to give you an intuitive feel for why we define the cross product the way we define it. So what you have right now is two vectors, right? And this is sort of my first goal in that after I multiply these two, I want to get a vector back. Because I already have a product that will give me a scalar back. That's a dot product. Most of you are already familiar with it. Here, my goal is to get a vector back. So mathematically, geometrically, what you are searching for is that given these two vectors, how would I define a third vector so that the direction of third vector is uniquely defined by direction of these two vectors? So the two vectors in geometry, there's a geometrical object that two vectors can define. What is that? A plane. It can two vectors. It's like two lines that cross each other. They can define a plane, as long as they're not collinear. Good. So, all right. So I want to be able to describe the direction of a plane. How do you describe the direction of a plane other than drawing the plane? Yeah. So when you want to associate a direction with a plane, we have been doing this already so far. We did it with the Gauss's law. If you have a plane and you want to describe the direction of a plane with a single vector, you do that by defining, well, vector that's coming perpendicular to the plane. Now here's the difficulty. You have two vectors that can be perpendicular to this. It can be coming out of the plane, or it can be going into the plane. They are both perpendicular to the plane. They are both valid normal vectors to the plane. So how do you pick? So this is already an improvement. Before that, you had like if you are looking for a vector within the plane, there's an infinite number of them. But by focusing on the vectors that are perpendicular to the plane, I've narrowed my choice down to two. But I still need to pick one unique direction. So for those of you who remember Physics 4a, how do we pick that unique direction? Right-hand rule. Is there anything special about right hand? That it's the correct one? Why is that the correct one? Yeah. In other words, why is it right-hand rule and not left-hand rule? Okay, raise your dominant hand, please. Okay, I count about. No, you don't have to be embarrassed. Yeah, so when you look at the dominant hands raised, about 90% of you are right-handed. That's the statistic. So that's really the only reason we have a right-hand rule. It could have easily been a left-hand rule, but because we are the 90%, we decide to oppress the remaining 10%. No, just kidding. But I'm trying to tell you it's an arbitrary rule. So we had to pick right hand or left hand to make a unique choice. And we make an arbitrary choice that it's going to be the right hand. And the only reason it's right hand, sort of an accident of history. Who knows why 90% of people are right-handed? If you read anthropology or something, some people suspect it started with the invention of tools. But whatever. So the fact is that there are more right-handed people than left-handed people. So it's easier for us right-handed people to use our dominant hand to apply this rule. That's why it's a right-hand rule. So people who are left-handed, all you have to do is, learn to use your non-dominant hand to apply this rule. So it does come down to, using what we know about mathematics, using what we know about geometry, we were able to narrow the choice of vectors down to two. And what I'm trying to tell you is that there's no law of nature that will narrow it any further from there. We simply had to make a choice so that we have a common convention to use among all humans. Maybe Martians use left-hand rule, who knows? So this is how you use right-hand rule. This is the basic right-hand rule. In this class, you're going to actually see 2 or 3 more shortcuts of right-hand rule in particular context. But this basic right-hand rule is what I stick with. And in your textbook, you might see the versions that use multiple, like 3 fingers. I never use that one. If you want to use that, great, do it. I never use the 3-finger version. I always use the one with my whole hand, because this one will also morph naturally into the shortcuts later when we introduce them. So this is the right-hand rule. I orient my hand so that it goes in the direction of the first vector, or I put the hand in the direction of the first vector, and I orient my hand so that I can bend my fingers in the direction of the second vector. So that means I have to turn it this way. So once I have my hand oriented correctly, my right hand oriented correctly, so that it's pointing in the direction of first vector, and when I curl my fingers, it bends my fingers bend in the direction of the second vector, then the direction of the thumb tells me the direction of the A cross B. So the thumb is either coming out of the board or into the board. Those are my two choices. And here, what my direction of thumb tells me is that C must be coming out of the board. So C is coming out of the board. Right? So that's the right-hand rule. That's the basic right-hand rule. And as we get into magnetism more, you will see a couple shortcuts that, that's useful, but I want you to be solid in the basic right-hand rule first. So let me actually draw a few combination of vectors on the board and have you do this exercise, in the next 5 minutes or so. Check with your neighbors, and I want everyone to get a chance to practice this, because you can, hear and see me do this all day long. But if you didn't try it yourself, you'll kind of forget it, or there'll be some source of confusion that you don't address now. So let me just draw. Let's see. Let's do 4 examples. So 4 is a bad number. Let me do 5. 2, 1. 4 is a numerologically unfortunate number. I would do 8, but I don't think I can come up with the 8 examples. Never mind. No one here pays attention to any kind of numerology? All right, so let me do A, B, and just for fun, let's say these two are perpendicular. And A, B, A, B, and I'm going to try to draw it the three-dimensional vector. Everyone here remembers the notation that this means out of, and this means into. Yes, everyone remembers that? Let me write 2 vectors here each using that notation. So my, let's say A is going into the board, and my B points this way. And let's say my A comes out of the board, and my B points downward. All right, so 5 examples. Hopefully, it'll take you 5 minutes or so or less to figure out direction for all 5 of them. When you get an answer, compare it with your neighbors, and we'll come back to go over answer for all of them as a class. Are you guys all done 1 through 3?
You were done.
Yeah. Okay. You are talking about the 4 and 5, right? Okay. Everyone done 1 through 3, right? Yeah. Let's talk through 1 through 3 first. So the challenge with 4 and 5, for those of you who are still thinking through, is that you have to think 3-dimensionally. So 1 through 3 are easier because you are dealing with essentially only 2 dimension. All these vectors are in this one single plane. So let's get through this first, and then I'll give you a couple more minutes to wrap up discussion on this and come back to this. So 1, what is the direction of A cross B? Out of the plane. So this is the plane you are dealing with. So your choice is always going to be, is it coming out or is it going in? So here, A, so this way, so A cross B, it's coming out of the board. All right. What about 2? Out of. Did anything change from 1 to 2 in terms of direction? So what changed in terms of, because A cross B here probably isn't the same as A cross B here. What changed? So the angle here changes. What does that affect? Magnitude. Because if you remember, A cross B, the magnitude of it was the magnitude of A times magnitude of B times sine theta. So if this angle theta decreases from 90 degrees, that'll make the cross product smaller in magnitude. But in terms of direction, it's still the same direction. It's still out of the board. Good? What about A cross B here? You sort of find your way, A cross B, so it goes into the board. So, if you got 1 through 3 correctly, then you're on a good step. 4 and 5 are going to be challenging because you have to think three-dimensionally. Before I give you a couple more minutes, let me just give you a hint. One main property of the cross product that A cross B is its key property. That in fact it's a defining property. Is that it's perpendicular with the vector A, and it's also perpendicular with the vector B. Whatever the cross product is, it has to be perpendicular with both of these vectors. You see that it's true here. Whatever vector is coming out of the board or into the board, it has to be perpendicular with any vector that's within this plane. The thing that makes it difficult here is it makes it difficult for you to see the plane here, because the plane of A and B is not the board plane. But when you get the direction of the vector, that should still have this property. It's perpendicular to B and perpendicular to A. So a couple minutes to wrap up. Some of you are still talking about it when I interrupted you. So, and then we'll come back and wrap this up. Are you guys done? Yes? Okay. So let me draw the answer on the board. So A cross B, this, wrong color. I meant to grab green. A cross B, this should be the direction for A cross B. Note that it's perpendicular to both vector A, which is coming out of the board, so it's perpendicular to this vector, and it's perpendicular to B. Hey, did I? It's into, yeah. So let me go through this. I take my right hand, orient it so that it's going into the board. I can turn this any way around, but I turn it just enough so that when I bend my fingers, it'll go in the direction of B. So the direction of the thumb is roughly the direction where A cross B is going. But really what I'm going to do as I draw this, I'm going to make sure that this is perpendicular to B. Because as long as I draw this on this plane, it's automatically perpendicular to A. So what I care about is it perpendicular to B? The other thing that may help you visualize it is, it helps you visualize if you visualize the plane of those two vectors first. So this is A, this is B. So, so imagine the plane that's defined by these two. Then A cross B has to go perpendicular to this. It's either going this way or coming out this way. And really, so you cannot put more burden on right-hand rule than this. The only thing right-hand rule is designed to tell you is of those two perpendicular directions, which one. That's really the only thing it's designed to tell you. So when I do A cross B, then it's one on this side, not one on the other side. Okay. So that's 4. 5. Okay, so this should be the direction of A cross B. Yeah? Coming out of the board, sort of pointing this way. And I orient my hand so that I can bend downward, thumb points to right. So here. Yeah. So that's it. Once again, the examples 1 through 3 are reasonably simple. Hopefully everyone got that. 4 and 5 is where it gets tricky. Takes practice. So one of the things that all of this tells you is that to describe magnetism, magnetic force, you need the full 3 dimensions. So everything we have done up to now could have been done in 2 dimensions. We draw electric fields in 2 dimensions. We draw equipotentials in 2 dimensions. But once you get to magnetism, you have to come face with the fact that we live in 3-dimensional world, and there's no way to describe this phenomenon without using all 3 dimensions. So let's wrap it up here. So what we observed experimentally was that as the current flows left to right, is this still on? Yeah. As if the current flows from left to right, the force on the wire is it pushes it out of the board. All right. So let's try to reason it out through here. So when I do V cross B, what direction does the V velocity cross the magnetic field B go? It goes into the board, right? So I have to explain why the force comes out of the board. Why does it come out of the board? because of this charge. Electron charge is a negative charge. So, this charge here is minus E, not plus E. So, because it's a negative charge that's moving. So it's the same thing you had with electric field. In fact, I would tell you that this particular combination here, this is more similar to electric field than anything else is. The quantity of V cross B is the quantity that you can almost compare directly to electric field. And we'll talk about that more later. Now, what if, so you could say the thing about assigning negative charge to the electron is an accident of history, right? So when I describe my current this way, it could have really been a positive charge that's moving to right. In that case, do you get the same result when you describe the force? So V cross B points out of the board, but this time my charge will be positive. So with this, it will be positive E. So yeah, when you're looking at force, it doesn't matter if the moving charge is negative or positive. So that's really that's a sort of semi-justification of what I said earlier when we were doing circuits. That often we pretend that the current is a positive charge moving in the direction of current, because almost always that doesn't matter. Even when we are dealing with the magnetic force, it still doesn't matter. The direction of magnetic force is the same, whether we are describing positive charge moving with the current or negative charge moving the opposite from current. The one exception that you should know is something called the Hall effect. If we have time today, I think we will have time today, we'll describe something called the Hall effect. That is one exception where the actual sign of the actual charge carrier does matter. All right, I probably should write down a few more formulas. I don't know if I have time to derive it, and it almost doesn't matter. So let me write down two different expressions for magnetic force that you will see on that corner there. So that I can refer to it for the rest of today. So the first one I will write down by copying what's there. That's what you could call the very basic expression, that magnetic force is given by Q V cross B. The cross product here gives you a vector. Multiply to charge, scalar, gives you a vector. And what I really want you to be reminded of as you look at this expression is that electric force is charge times this V cross B. This will sort of become like electric field. That's what I want you to be reminded of when you see this. Now, most of the time when you are dealing with magnetic force, you won't be dealing with a single charge. I mean, there are experimental situations where you do, but like we did this demo here, you are not really dealing with a single charge. You are dealing with current that's flowing in a wire with some length, with some extent of magnetic field. So let me write down an expression that's useful in a case like this. So you can look at the textbook for how you get to the second expression from the first one. So the magnetic force on a wire, on a current carrying wire, is going to be proportional to how much current is flowing. That's why here, if I change this setup so that, I don't know how I do it. Let me do it this way. Let me turn down this knob so that it doesn't let as much current flow. So when the current is less, right now about a half as much as what it was before, and when I set it up, now the magnetic force isn't as much. It doesn't move as much. Like it barely moved a little bit, right? So the magnetic force is going to be proportional to current. So here will be current. And you need some kind of quantity that will give you both the magnitude and the sense of direction. And I will write down the expression first, then I'll draw a figure to define the terms. It'll be L, length of the wire as a vector, cross magnetic field. So I should really draw a figure to especially define this L, because we are not used to dealing with the wire as a vector. It's something we define specifically for this. So let's say you have magnetic field pointing upward like last time. And let's say I have a current carrying wire which is placed in this space. Let's say going this way. Then the vector L, it's related to the length of the wire, obviously. So if the wire is, let's say, so if you are looking at, I guess we can kind of imagine this to simplify it. So we can imagine that this wire is part of some loop or something, and there's a wire coming into the board, and then it turns here, and current starts flowing this way. And then let's say, then it turns here, and then it comes out of the board again. Okay? So if you are interested in, let's say, magnetic force on this segment of wire that you see, in that case, the magnitude of L is the length L, as you would have guessed. That's the magnitude of L. And the direction is, this is the direction of L. So if the current is in the direction I drew, then the vector L would look exactly like this, going from this end along the direction of the wire, aligned with the direction of the wire, in the same direction as the current. So this would be my vector L. It's kind of intuitive, I hope, that nothing I'm saying here is counterintuitive. But if you want to be precise and make sure that it's unambiguous, that's how you would define L, the same length as the actual length of the wire, and pointed along the wire so that it's going with the current, not the other way. So, and I won't do the derivation since that'll take precious time, and I won't have enough time to go over maybe a couple examples today. But yeah, if you want to see where this comes from, you can look in the textbook. And the way you do is you express this current in terms of the charge density of the things flowing. And you can look at it in the textbook. Yeah.
What force is this again?
This.
Magnetic force on the wire?
Yeah. So this is the force that you are seeing here.
Yeah.
So I mean, this wire moves for some reason, right? So here, the length of the wire you would use is the length that's within the magnetic field. Yeah. But yeah. So magnetic field, magnetic force. On wire by magnet. So I guess maybe a better, the more common term is magnetic force on current carrying wire, because it's not these two that says if there's a magnetic force or not. It's that times the current that says that there's magnetic force. Yeah. That's actually one of the reasons this is kind of hard to demonstrate in class, because you need a fair amount of current to even produce tiny amount of force, you see. And generating current greater than 3 ampere kind of takes big power supply, and that I don't have. Yeah. Okay, I think we have enough time for some of the examples I want you to go through. So let me go over this example of loop of current so that we have some context for thinking about different interactions between magnetic field and, current that we are going to look at. So this is the setup that I want you to imagine. I guess if you want to see a physical prop, then this is sort of what you should imagine. I have this magnet sitting here. Imagine it's a much bigger magnet that's producing magnetic field pointing up. And what I could have is a current carrying loop, as in this is a loop, right? And I could cut off a section of it, attach a battery there, so there's a current that's flowing around in a loop. Now, if I place this loop over that magnetic field, what kind of interaction do you expect to see between this loop and the magnetic field? That's the question. You are wondering if it's rhetorical or not?
Force?
Okay, so you might expect there to be net force on this loop. Let's carefully analyze that. So for the purpose of drawing it here, I'm going to make it a rectangular loop. It's easier to draw that way. So let's say I've been using blue color for magnetic field. So call this current carrying loop in magnetic field. So let's just take this as an example. Magnetic field points upward. And I'm going to stipulate that this is a uniform magnetic field. That it's a uniform magnetic field. It's the same strength of the magnetic field all the way throughout. And we'll talk about later how you might make magnetic field like that. For the loop that I was holding up, I guess this is how you can draw it. So I'll have to draw it in 4 segments. So there's a segment 1, the front segment. Let's say current is flowing from left to right there. So call that front segment 1. After current flows from left to right, then there's a loop that goes into the board, or there's a segment that goes into the board that continues to carry the current. So this is segment 2. And then on this side, there's a section that's carrying the current from right to left. So that would be segment 3. And then there's a final segment that brings it back to the starting point. Segment that's coming out of the board. Segment 4. Good? So it's an exercise on, all right, let's say it's a square loop. In that case, is everyone convinced that the magnitude of magnetic force will be the same on each one of these segments? If it's a square loop? Yes? All right, let's make it square loop. So it's an exercise on figuring out the directions of magnetic force so that we can see what the net force on the entire loop is. So loop 1, what is the direction of magnetic force? Looking at this, L probably goes left to right. So what's the direction? L cross, yeah, out of the board. So I need to, let me draw a free body diagram here. So free body diagram, this is my loop. So the force that's due to 1 will be out of the board. So there's force coming out of the board due to on the segment 1. What about force on segment 2? Is it in the plane, out of the plane, into the plane, in the plane? In the plane, what direction? Pointing to right, right? Yeah. So the force on the segment 2 is pointing to right. What about force on segment 3? Yeah, into the board and close B. So, all right, so this is the force on segment 3. What about force on segment 4? To the left, right? Yeah. So this is on segment 4. So this would be the side view. And so, you know, with the magnetism, once again, it's 3-dimensional. It's hard to represent it clearly in 2-dimensional picture. So if I drew one more picture that's a free body diagram of the top view, as in you imagine going over here and looking down from above. From the top view, this would be the free body diagram. 1, 3, 2, 4. So what do you think of the net forces? 0. Oh, does it sound right? That if I have a current carrying loop here, that it doesn't interact with the magnetic field, that it has net 0 force? It might not strike you as intuitive, especially if you know anything about a motor. So we are going to look at motor later on in the semester. All that a motor is a current carrying loop placed within the magnetic field. And somehow it rotates. I think I actually oriented this kind of wrong for that. Let me imagine this loop turned around. So yeah, this is in the part that's sometimes called dead zone. So let me imagine it turned around this way. So that now I'm still dealing with the same loop, but it's oriented around. So let's say, let me do it in different color, red. So if the loop is oriented around, so the segment 1 becomes this segment. Segment 2, well, it's still going into the board. Segment 3 brings it back down. And segment 4 is still coming out of the board. All right, let me draw that. Let me draw the, yeah, let's draw it here just in red. So force on segment 1. Any force on segment 1? No, because L is parallel to B, so 0 force, or sine theta is 0. And the same thing for 3. So 1 and 3 are 0. What is the force on segment 2? Yeah, still the same as what you had before. Let me draw it here, actually. So force on segment 2 points to right. This is force on 2. What about force on segment 4? Left, the same as before. So if we are looking at net force, has anything changed? In terms of net force is still 0. This will balance out this. But something has changed, so that if I place a loop this way and let go, it will start to move. How does it move? Yeah, it starts to rotate. So this is an example of a torque on a current carrying loop due to a uniform magnetic field. So the result here is that there is a torque on current carrying loop due to uniform magnetic field. And even though we did this for a square shape, turns out that if it's a loop of any kind, as long as you are dealing with a uniform magnetic field, net force will always be 0. As long as you are dealing with a uniform magnetic field, your net force will be 0. But depending on the orientation, sometimes you will get a situation where net torque is not 0. So this is the basis of the motor. That actually there's a lab for motors a little bit down the line. You're going to look at that. But so what it takes to have a non-zero net force on a current carrying loop is to have a non-uniform magnetic field. And I think you might have some homework exercise actually based on that, where there's a current carrying loop and there's a net force on it due to magnetic field, because a portion of the loop is in the magnetic field and a portion is not. In that case, you can have a net force. Okay? All right, so that's one example I want you to start seeing, because it's a basis of a physical picture that you'll see more.
The magnetic force in a very most elementary interaction between a most elementary object that responds to magnetic field is and the most elementary object, it's not magnetic charge because they don't exist. It's going to be an electric charge, and these electric charges interact with the magnetic field in this way. This is the most elementary interaction. The magnetic force is charge and this vector cross product with the magnetic field. And this underlying mathematical structure leads to features that you will see that really requires a three-dimensional treatment. So I was looking to see what would illustrate that. And I think the best thing I have is this. I thought this video would be something that at least replaces that partially. So I'm not going to play the whole 14 minutes of it, but let me play a portion of it to show what I mean. So let's see here. So I turn again so that I can point to different parts of the apparatus before you see the whole thing. So where it was aimed at, that's the main working part of the apparatus. Once I turn the lights off and turn this properly on, then you'll be able to see what it does. I'm moving this around so that you can see the coils. These are the coils that generate the magnetic field. They are in an arrangement called the Helmholtz arrangement. I will have it be part of your lab activity where you go through the analysis of magnetic field due to Helmholtz coil. So these coils produce magnetic I'm gonna skip ahead for a bit. So there's a portion where I illustrate the beam and turn on the coils to bend the beam, and that's a more kind of clinical presentation of the effect of the magnetic force. That I actually have a simulation that I think that'll decently show that. So what I want you to show was, let's see, I think. So around, oh, maybe, let me do, I think around here I'm moving around. So let me skip to that and turn back on the sound.
It's moving in circle. It kind of, if I move this around a little bit, you see the circular path comes, you can see that the circular path comes back to where it started. Now, I can do this. I can turn this bulb, I can tilt it a little bit so that the initial velocity of the charged particle is not perpendicular to the magnetic field. Then see what happens. That's the helical path that your textbook talked about. Let me increase the magnetic field a little bit so that there's a more room to for the helical path to happen. So with this increased magnetic field, that's the helical path that the electrons follow. So interesting. So for doing purpose of making measurements for this lab, I would make it sure so that the path falls back to itself. It doesn't follow the weird helical path. So
Not weird, interesting helical.
not weird, interesting helical path. So that's pretty much it. I mean, this is a fun lab to do in person, and there's a lot to learn and be careful about measurements. I'll try to capture some aspect of that in the activities that I still need to write up. So for today, what I want you to end with is some demonstration of a magnetic force. I mean, you have some in the recorded lecture videos, but while I have this apparatus, there's actually some things I can demonstrate. So, so this is yeah, you can already see I'm bringing something new. This is a neodymium magnet. It exerts a fairly large magnetic force. It produces a pretty large magnetic field compared to its size. And this is like a bar magnet, more or less. And I can use that to apply force on that ring. Like I can bring one pole closer, reducing the magnetic field, so making it so that the beam doesn't bend as much. Oh, wait, you can't really see it. Yeah, maybe. Or I turned it around and you can increase the magnetic field so that the beam curves more. And there are other fun things you can do. You can, I guess this isn't quite strong enough. You can use this magnet to repel the beam. And there's I think I posted somewhere about the magnetic bottle. That's the principle. This is a bigger, stronger neodymium magnet. There's a principle on which this repulsion works. The current, the curious or the interesting thing here is that this repulsion, it happens with both poles. So right now I have one pole which is repelling the beam away, and now when I turn it around, you can see that it's turned around because the way the beam distorts is different. It's the other way, but it's still repelled. It has to do with the magnetic field gradient, and it's kind of a cool thing. But I think this is better to see and play with it in person. Just looking at it through a video, I imagine it doesn't have quite the same impact.
So let me have that serve as an advertisement for our next week's not next week, sorry, keep saying that. Next in-person lab, which is based on this apparatus, and I have those strong magnets. And when you are manipulating the setup with those strong magnets, you also you can actually feel the force with which the electron pushes back on your hand. It's it's one of those things that you have to experience firsthand. So yeah, that's the this is the illustration of the kind of the complex. Not it's not really complex, but maybe unexpected, more rich, interesting geometry of interaction between magnetic field and moving electric charges, which is the most elementary object that can interact via magnetic force. Um, and on that line, I thought, what would this is a fixed video. Like, it takes a lot of work to change it. That's why I'm inviting you to come to the lab. Um, what I thought, and charge and magnetic field is one of those things that there aren't that many good simulations out for. I think it is quite difficult to simulate well, because really what you have to simulate is a three-dimensional environment. So if it's like doing a 3D modeling, you have to be able to click and drag. That takes quite a bit of user interface work. And anyways, I looked around for a bit, charging a magnetic field. I didn't really find the exact thing that I wish I had. I think this is maybe the closest. So I mean, not exactly. I mean, it's quite simplistic simulation, but it at least gets at that gets at the different variations you could see. So, so right now, what I'm simulating is, well, nothing's happening. The charge is at rest. There's no magnetic force, so nothing's happening. Okay, so there's that. We can make it a little bit more interesting. The charge could be moving relative to the field, or it could be moving parallel to the field. That also nothing really interesting happens. Charge just moves. It looks like it's moving under zero net force. Yeah. So let's make it more interesting. And this comes from where the magnetic force on a moving charged particle is V cross B. It's a cross product of the velocity vector and the magnetic field vector. So when those two vectors are parallel, the cross product is zero. So for maximum magnetic force, you need the force to be you need the field to be perpendicular to the velocity. So this is illustrating the picture where, so the velocity of these particles are still the same. They are moving up on the screen, and the direction of magnetic field has changed. It's pointing into the screen. So if you use right hand rule to the V cross B, then you get that the quantity of V cross B is pointing to the left, your left, which is also the screen left. um, so for the positive charge, the force it feels will be in the direction of V cross B. So this will start out bending to the left. For a negative charge, in the expression for the force Q, the charge times V cross B, if the charge is negative, that reverses the direction. So this starts out bending to the right. And a chargeless particle will also feel no magnetic force. There's a connection between electricity and magnetism that will become more apparent as we go on. So let me just play the simulation, pause it in a little bit. Now, one thing you will see is that these charges are not just bending to left and bending to right. And this is the interesting feature of the magnetic force, because it's a V cross B. It's not in a constant direction. If there had been a horizontal electric field, then this would go in a parabolic shape, almost like a version of a projectile motion. Same thing with the discharge here. With the magnetic force, as the direction of velocity changes, direction of magnetic force changes as well. So it changes in a way that velocity and magnetic force are always perpendicular. And if you think about what other forces have you seen where force is perpendicular to your velocity. I hope that reminds you of a centripetal force. And if you recall the coverage of centripetal force from physics 4a, centripetal force is not it's not a particular type of force. I prefer to liken it to a type of net force. It's a kind, so, net force. What you get when you add up all the forces, and you call that net force centripetal force when certain conditions are met. And one of the conditions is that the force is perpendicular to the direction of velocity. And that has impact on the kind of a trajectory, whether the force can speed up the charged particle or not. And that's what we're seeing here. As the time goes to infinity, these two charges will be going in circles, and the neutral charge didn't feel any force, so it went off the screen. Let's see what else. Oh, let's try doubling the speed. See what happens. Yeah, larger radius. Okay, would you have guessed that? I think it's not immediately obvious because you got competing things here. So let me try to write this out. So when you have larger velocity, you would expect a larger force because you have the expression for the magnetic force being charge times V cross B. So if you're just focusing on, hey, I have a larger velocity, so I should have larger magnetic force, then it's easy to think that your particle should draw maybe a smaller trajectory because the magnetic force is greater. Now, you can't stop your analysis here because you are dealing with the circular motion. You also need to deal with the expressions dealing with the centripetal acceleration. So the centripetal force is mass times the centripetal acceleration, v squared over r. So you take a look at that, take the magnitude of this force, Q, V, B, and you realize, even though the magnetic force went up by a power of 1, if you wanted to keep this particle moving at the same radius, as your velocity was maybe doubling, because this is going as a square, not just the linear power, amount that your force increases is not enough. So if you solve this for r, you should get an expression that says something like r is proportional to v, and that is what you're seeing here. When you double the velocity, the radius that this circle goes in is doubled, and it's a combination of two competing factors. That your magnetic force does increase, but the amount of centripetal force that's needed to keep the path in a particular circle of some radius, that also increases as a square of the velocity. So, yeah. And I think that's more or less it. We can play with other parameters, but I don't know how much interesting that is. And this is kind of a visualization. Imagine you had, three ions. I don't know, singly ionized, doubly ionized, triply ionized oxygen, for example. Then this is what you could see, maybe. I think the challenge would be keeping them ionized. Or you could have the same charge, but have them come in with a different velocity. I think experimentally this is easier. There are things called velocity selectors that can select the particular velocities of particle beam. Now, I hope you notice something interesting here. So these particles are moving at different velocities, and they are moving at different circles of different radius. But as you look at it, they remain in perfect sync. And I think it's natural to ask this question. Is this accidental, or is there some way that this must happen? And my quick answer is, and this is the only reason I would be bringing this up, is that yes, there's a reason that they have to work this way. And I won't go through the whole derivation, but I'll just give you the phrase that you can search. And I think this is also covered in Portable TA. The phrase you can search is something called the cyclotron frequency. And this remarkable, I don't know, coincidence that in this circular motion that's governed by magnetic force, that this frequency of revolution doesn't depend on the radius or the velocity of the particle. That fact is used in particle physics to help accelerate particles in like a circulating storage ring. And this remarkable coincidence also kind of goes away when you get to high enough speeds that you have to worry about special relativity. But up to a sizable fraction of speed of light, this is an effect that's really practical in particle physics. So I think that's probably everything about magnetic force that I want to and can cover. Let me just check to see. I will have left some notes to myself to do that. Oh, magnetic bottle. I guess let me just flash this briefly so that I can show where it's coming from, and maybe I can get a screen grab for later on. I just scanned in a textbook that I used when I was undergrad. I think there's a past virtual class session where I showed the people this textbook. This is what I used when I was taking this level of physics. I really like this textbook. This is also cheap. I think I got this particular copy for like $5 because 10th edition is out of date, but it's physics. It doesn't change that much. So, and I was assuming this forever that every textbook covered this topic because when I took physics, it was covered. I really enjoyed that coverage, and it was only when I was teaching physics for B for like second or third time that I realized, oh, this isn't really covered in other textbooks. So there's the textbook that we are using this semester, which doesn't cover this, and it also wasn't covered in Giancoli, which is the textbook that UC Berkeley uses. So it's I guess the way you refer to it is as a magnetic bottle. It's a way to trap charged particles within a region, experimental region, without using any material. So this is a way to trap, like this could be a positron, an antiparticle of electron. You can't store that in any physical bottle because when the positron collides with electrons in the physical wall, they will undergo pair annihilation. They will disappear. So you can't do that, but you can trap positrons within a fixed region using magnetic fields. And it's quite amazing how it works. If you imagine these particles starting out with some velocity that's perpendicular to magnetic field, then as they move in either way, as they drift a little bit to the left or drift a little bit to the right, they will experience this restoring force. That's kind of how V cross B works out to be. When you imagine this inhomogeneous magnetic field, strong at the ends and weaker in the middle, that the net force on these particles will tend to push it back towards the center region. And in fact, this is what you saw in the video that I played. You are basically seeing the one side of this magnetic bottle. And you can imagine if there being another strong magnet on the other side, then between those two, they have a possibility of trapping particle between those two strong magnets. And yeah, so I'm pretty sure this is not covered in our textbook. Let me just search to be sure, because I think I remember checking this in some semester before, and I don't remember seeing it in our textbook. So they do mention magnetic bottle, but I don't think yeah, I mean, they have this picture, which, all right, it's a kind of trapping also, but they don't have that nice picture that you see my other textbook. Yeah, so So anyways, this picture, I just wanted to show this picture because apparently it's not that commonly shown in other textbooks, either ours or textbooks that other people use. So.
I think what I have enough time for now is the example of Hall effect. So this is a single case where the sign of the charge carrier actually matters. And there's a reason we care about Hall effect. Anybody here know anything about semiconductors? Yes, no? Different types of semiconductors? Yeah, I'll do a brief introduction. So, actually, I guess I don't remember too much about semiconductors either. So, if you're dealing with a piece of metal, where are my rods? If you're dealing with a piece of metal like this stainless steel, then charge carrier here is electrons, negative charge, like no one's doubting that. So if you had a piece of metal, then charge carrier, the free charges are the free electrons. So it's the free electrons that are moving around. So charge carriers are negative. Like, all right. The more interesting situation happens when you are dealing with the semiconductors. So with the semiconductors, there are two different types. And I remember their names. I don't exactly remember which is which. There's an N-type, and there's a P-type. Once again, I don't remember which is which, because that's not really my field. But let me give you a description of the model of conduction in these two different types. One of them, it's just like with the metal. As in one of them, the way you would describe conduction is that you have some electrons, free electrons hanging around, and they are the ones that are moving around, right? The difference between this case and metal would be, and this is the reason it's called a semiconductor and not conductor, is that there's just so fewer of these electrons. So in metal, you might have an entire very high density of these electrons that are free to move around. In a semiconductor, there's very few of them, and in fact, this number of the charge carriers becomes one of the limiting parameter for what is the effective resistance of the material. Here's the other picture of the other type of the semiconductor. Once again, this is either N or P. I forget which. The other type, so this is the one type of semiconductor, and the other type looks like this. So you can imagine it as being mostly filled with electrons. Once again, I'm simplifying it way more than it actually is. There's something about energy levels, band gaps. I'm just skipping over all of that. So this other type of semiconductor, the way it works is, so it starts out with a description that's really similar to an insulator. As in, all the energy levels are filled. There's no electron that can actually move around. But the way this becomes a semiconductor is that there's a material that takes away some of the electrons. So there's essentially, in a space that's mostly filled with electrons, there's some spots that's missing an electron. Because it still doesn't change the fact that protons don't move around, and the only charges that can possibly move around are electrons. And in this picture, the charges that move around are still electrons, but so here it becomes easy to describe electrons that are actually moving around. Here, mathematically, it becomes easier to describe these holes in my complete electron sea, that these holes as moving around. So when this hole moves from, let's say, from here to here, then the real picture is that the electrons around them are moving around. But, well, could we describe this hole, which is technically positively charged compared to the rest of the material? Does it make sense if I describe this hole as moving? And when you look at this, you might say, oh, this is just some mathematical convenience. Like if you describe the current in this semiconductor as flowing, as this Hall, that's just mathematical convenience. The real charge that's still moving is still electron. This is the context where Hall effect is important, because this is one experimental setup that will distinguish between is your charge carrier positive or negative. And that's the experiment that's done with these two materials. And this gives one result that says your charge carrier is negative. This gives the other result that says your charge carrier is indeed positive. So in that case, that makes the case stronger that you can truly think of charge carrier here as being positively charged, rather than, I don't know, I sort of think of this like the geocentrism versus heliocentrism debate. As in, is heliocentrism simply a mathematically convenient way to calculate the positions of planets? Or is that the way things actually move? And with the Hall effect, it becomes easier to argue that the movement of the holes, that's the way things really move, not just a mathematical convenience. Anyway, so let me describe the setup. I only have like 4 minutes to finish describing. And so let me call this Hall effect apparatus. Hall effect apparatus. And in this example, it's going to be easier for me to draw the picture if I orient the direction of magnetic field perpendicular to the plane. So I'll say my magnetic field, which I've been drawing in blue, my magnetic field is, let's say it's pointed into the board. Okay? And I'm just going to draw a few of these here, but you should really imagine the entire space as being filled with uniform magnetic field that's pointing into the board. Okay, and what I am able to set up in this space is I can, place a conductor or semiconductor rather, for the case where it actually matters, and I can hook it up to a battery. I can hook up the left hand to a battery, let's say positive terminal of the battery, and the right end to the negative terminal of the battery. All right, what direction does current flow? Supposed to be from left to right, right? From positive to the negative end. So this is the direction of current. That is not in dispute at all. Like, that's how you define current. And so far what we've said is we don't really care if the moving charges are positive charges or negative charges. So let me draw the picture with the positive charges on the left-hand side, and picture with the negative charges, the more common picture on the left-hand side, and picture with the positive charges on the right-hand side, just to compare what happens in those two cases. So, okay, this is my dividing line. So on the left-hand side, it would be if a charge is negative. In that case, what it would mean is, all right, I have these actual electrons, or something that's like an electron, that must be moving to left. That's how I get the current that's flowing to the right. And the flip side of that picture is if my charge carrier is positive, then, well, I must have some positive charges here. I guess I'll just say plus E. Positive charges here, that's going in the same direction as the current. Okay? Yes? And what you guys already saw in class was that in both of these cases, the direction of force was the same, right? For the positive charges, you do V cross B, force points up, force is directed upward. Same thing here, do V cross B, V cross B. V cross B is pointed downward, but my charge is negative, so the force points upward. So up to that point, it doesn't matter if the charges are negative or positive. That would still say, all right, force is still upward. But the Hall effect comes in when you consider, all right, so what happens to these charges due to those forces? So if I say, all right, I have these negative charges that are experiencing upward force, then this is what I get. I have negative charges that accumulate on the top side of this conductor. which also means there must be because the whole thing is charged, net charge 0, there must be positive charges that accumulate down here. Right? And here, these positive charges are pushed upward also, which means there must be positive charges accumulating on the top surface here. And that also means there must be negative charges accumulating on the bottom. So when does this process stop? I mean, does charge accumulate on the top and bottom forever, or does at some point this stops? No, current will keep flowing. I'll continue to hook up this battery. I want this. So what determines that maximum? So I do believe there is an maximum. No, I'm looking at essentially, some kind of surface charge density. And I do believe there's a maximum surface charge density. That at some point you will reach an equilibrium where there'll still be the magnetic force that pushes these charges up, but something else will balance that out. What is the something else that might possibly balance that out? What do you get whenever you have charge separation like this? Electric field, right? Yeah, there's going to be electric field due to charge separation. That has nothing to do with the field due to voltage. It's just a field due to this separation of charge. There will be this electric field established here that points up. There will be electric field established here that points down. What do you have once you have electric field? Electric field over a distance. Not force, over a distance. Sorry, it's a bit of a vague question. I'm out of time. When you have electric field over a distance, you get voltage. Which means, so experimentally, you cannot measure this field directly, but what you can measure is you can hook up a voltmeter to the top and bottom surface here. And you can have a voltmeter hooked up to both ends and read the voltage difference between top and the bottom. Then, if you read that the voltage on the top is greater than the voltage on the bottom, then your charge carrier must have been positive. If you read the voltage on the top is less than the voltage on the bottom, then your charge carrier must be negative. So this is a setup that distinguishes whether your actual charge carrier is negative or positive. And when they do this experiment with this type of semiconductor, they get that charge carrier actually is positive. So, so you don't, yeah, it's so this is treated as though your true charge carrier are these holes that have, that are positively charged.